magnetic materials have different BH curve. So now computation of the hysteresis loss. I have to proceed very fast. I think you have already covered in 10 plus 2 standard, isn't it? Do you have covered in 10 plus 2 standard this topic?
Yes, sir.
No,
Yes.
sir. No, sir. No, sir.
No.
No, sir. What is?
Okay. Plus H is the magnetic field intensity, and plus B is the electric field intensity. This side minus B, and this side is minus H. So I am considering that L is the length of iron bar, and A is the cross-sectional area. And N is the number of turns of the coil. Actually, there is a solenoid type construction. The magnetic material is there, and a coil is there. Coil is energized. So number of turns is N. The length on the bar, that is your L, and the cross section, that is A. A is the cross section. And now the magnetic field intensity, the magnetic field intensity H is equal to, and if the current is which is flowing through the conductor, that is your I. So magnetic field intensity, that is Ni by L, ampere turn by the length of the magnetic flux path length, actually length of the magnetic material. Now you know that whenever the current is increased, say increment of current, that is Di. Whenever there is an increment of current, obviously there is a flux increment. I'm considering the increment of flux, that is your d phi, and the flux, the area of the cross sectional area is constant, so increment of flux density, that is your dB. Now you know that d phi, that is equal to A into dB. So this is dB is the flux density increment due to the current increment, and d phi is the flux increment due to the current increment. So induced EMF. So there is a small increment of current. Actually, current increment will cause uh, electric field intensity increment. Sorry, magnetic field intensity increment (DH). That is equal to N di by L. So very small increment of magnetic field intensity, there may have, actually the curve here is not perfectly okay. Now I'm considering very small increment of field intensity due to the increment of current. There is a flux increment. So if I consider this, so this type increment of field flux density, that is dB, and increment of field intensity, that is your dH. This is the increment of field intensity and increment of flux density. Now, induced EMF due to the change of flux linkage, the induced EMF E, that is equal to N d phi dt, the rate of change of flux linkage according to Faraday's law of electromagnetic induction. So that is equal to N into A dV by dt, Na into rate of change of flux density. But according to Lenge's law, it will oppose its cause, and cause is the increment of current, and uh, this induced EMF will oppose its cause. Cause is your increment of current. So there is an energy wastage. Someone is trying to join. So increment of current, there is some energy wastage, or that is manifested in terms of voltage into current into effective timing. So input energy, if you consider the induced EMF E and say instantaneous current is small I. I have already considered the instantaneous current is capital I. So work done for this increment of current, that is the cause of the change of flux linkage. So that is dW, work done. So that is the energy which is required for this increment. So energy is required means the effective voltage is E, instantaneous current is I into dt. So if you consider the instantaneous current, the total current, that is I, say instantaneous current is small I if you consider here. If you consider the instantaneous current is small I, so induced EMF E into small I into dt, that is your energy. That energy is manifested in terms of work done. So according to Lenz's law, it is the cause, there is the change in current. So actually, the induced EMF that is created, that is the change in flux linkage, that is due to the change in flux linkage. So that will be equal to NA dB by dt, that is your EMF. And for this for this current, that current you can consider that instantaneous current I, that is equal to HL divided by N. So that into HL divided by N into dt. So actually, that is A into L, that is the volume of the effective flux path, into H, magnetic field intensity, into dB, change of flux density. So H into dB, that is your area of this small portion. Actually H into dB, if you consider the total area of the shaded area, so if you consider this from increment, if you consider from initial to this point, so this total portion will come into dB is increment. So if you consider this from the initial point, so this point to this point, so then dH will be this portion. So this dH into dB is the total area. If you consider from the initial moment when the current is 0, then current is incremented to this level. So this portion to this portion, if you consider. So the flux change will occur this total area. So this total area, total effective area, if you consider from the initial moment, the total effective area is this. So then, for one complete cycle of magnetization, actually magnetization means the current reversal and flux reversal. When the current reversal means the current direction changes from the initial moment. So if the current is plus I and then it is reversed, that is minus I. So flux change plus phi to minus phi. So this current reversal is taking place. So the total for complete cycle, whenever there is a alternating voltage is applied. So you have to consider, if you can apply alternating voltage, then you have to consider one cycle of reversal. So if you consider there is a switch, there may have some reversible switch. Reversible switch is connected. You can alter here. DC voltage is there, but you can alter through the current change through the reversible switch. Plus I to minus I. Then there is also flux reversal. So this and one complete cycle is carried out. So the net energy that is utilized for this reversal of magnetization, that is the complete cycle, that is W is equal to AL into close integral of this H into dB. So if you consider the complete cycle, then your total cycle will be, pH loop will be completed. So that will be equal to the net energy spent in a complete cycle. So the net energy spent over a complete cycle, net energy spent per cycle. So if you consider W by AL, then HdV, the total closed integral of this HdV, that is equal to net energy spent per cycle per unit volume of the magnetic material. So unit is joule per meter cube per cycle per second. Actually, this is the unit of the wastage of power. That is joule per second, that is in terms of watt. So the unit will be
Sir, here up to which part we are considering as the cycle?
which part means the total cycle completion.
Sir, that means only H into dB or like the entire cycle?
Whenever you consider, say this point, okay, you are incrementing current. So there may have some increment of increment of this current change. If there is a current change, if you consider from certain point to this point, so there may have some increment of current, and due to increment of current, there may have some increment of flux density. So if you consider this, if you consider this portion, then due to this increment of current, so this is the area of the strip from this point to this point. If you consider from initial point, so then the total area is there. But if you consider this point to this point, so this is the increment of flux and flux density due to the increment of current change. And there may have some increment of field intensity also. So this small area, this covers, that is the energy wastage for this increment of current, the work done due to the increment of current. So if you consider the whole cycle means, so this total portion, when there is a current reversal, complete reversal of current, that is plus I to minus I. So from the initial moment, if you consider when the cycle is completed, then current reversal, firstly the current is uh, incremented from 0 point to a certain maximum point, then maximum point to 0 point, then again reverse direction current increment, and then current goes to 0. So actually, if you consider first cycle, then from 0 point it is started. So it reaches this point, so plus I. And then it follows this path. Then in the negative side, so there is a negative increment of current and negative increment of flux. And then I have already explained this BH loop. So complete cycle means this complete loop completed, or one loop has been completed for one cycle, one reversal of cycle. So that is called the reversal of magnetization. So this reversal of magnetization causes the area of the BH loop, and this area of the BH loop, it measures the hysteresis loss. You understand my point?
Yes, sir.
Sir,
Hmm.
sir, H is यहाँ instantaneous magnetic flux intensity, na? As the current is instantaneous.
Yes, and the current is instantaneous. H is actually H is the uh, for current I, the magnetic field intensity is H. So actual magnitude is Ni by L, whatever current is there.
Yes, sir. N and L are constant and I is instantaneous. So H will be also instantaneous.
Yes, whenever I is instantaneous, then H will be instantaneous.
So, sir, here in the formula H represent which instance?
For this formula, when the current is I, the field intensity is H, and the formula is Ni by L. If the current is Di, then instantaneous change in field intensity is Dh. Actually, N and L are constant, so Di is changing, so Dh is also changing.
Yes, sir. Yes.
So this is your formula. Actually, this is your total complete cycle, and this is your this is the magnitude of the uh, hysteresis loss per unit cycle, per unit volume of the magnetic material. So different magnetic materials are there, and different magnetic materials are having different hysteresis loop. And if you consider hard steel is there, then there is a hysteresis loop. Different specimens are there. So smaller the hysteresis loop area, lesser will be the hysteresis loss. Different material having different hysteresis loop. If you consider hard steel, the hysteresis loop is quite more area. And if you consider the wrought iron, the residual flux density is comparatively more. But if you consider the silicon steel, if you consider the silicon steel that is made by all the electrical machines are made by silicon steel, transformer, electrical motors are there that having low hysteresis loop area, very low hysteresis loop area. Actually,
Sir,
yes.
sir, can you please superimpose the three graphs, sir, for better understanding?
Actually, I have two colors, black and uh, red.
Sir, use dotted lines for the third one.
So this is, say, hard steel. And for wrought iron, comparatively less hysteresis area. And if you consider this is for, say, and if you consider silicon steel, so the silicon steel hysteresis area is much less than your hard steel. So permanent magnet, these are belongs to this hard steel, and the wrought iron, these are used for sometimes making the yoke. Actually, yoke is the outer cover of the electrical motor. Hello. না, আমি এখন একটা ক্লাস নিচ্ছি, পরে কথা বলবো, 12টার পরে ফোন করো। So hard steel is usually used for hard steel material is used for magnetic material for permanent magnet. So widely used for making permanent magnet, and your wrought iron material that is used for making the yoke design. Actually, external it will provide the mechanical support to the electrical machine, and sometimes it also carries flux. But in case of transformer, actually, or the armature of the electrical machine, that is made by silicon steel, that is hysteresis loop area is very less. And actually, whenever there is a alternating current that is applied to a magnetic material, when there is a current reversal, there is a flux reversal. So, one say 50 hertz frequency is applied. So, supply voltage frequency is 50 hertz. So, 50 cycles per second is carried out. So, 50 number of cycles of hysteresis loops are generated. So, you can consider the whenever the number of cycles is increased or frequency is increased, then hysteresis loss is also increased. So there is also a hysteresis law. There is a Steinmetz law of hysteresis. Actually, the scientist Steinmetz, he computed the hysteresis loss. If you consider the hysteresis law of Steinmetz, so Steinmetz computed the hysteresis power loss. So as per the Steinmetz formula of hysteresis loss, that is pH, that is equal to nu, that is the hysteresis coefficient, into frequency, cycle frequency. Whenever alternating supply voltage is there, the cycle frequency, that is F. So F number of cycles are generated per second, and then B max is the maximum flux density to the power 1.6 into V, the volume of the specimen core. So nu F B max to the power 1.6. This 1.6 is the Steinmetz index. Different material having different Steinmetz index. So whenever Steinmetz index is more, then hysteresis loss is more. Whenever Steinmetz coefficient is more, this is your coefficient. This is your frequency, maximum flux density, and the volume of the specimen. So different Steinmetz index and different Steinmetz coefficient is there that dictate the hysteresis loss amount. So obviously, since the uh, silicon steel having cold roll grain oriented silicon steel, CRGO, it is termed as CRGO, cold roll grain oriented silicon steel, having low hysteresis coefficient and low and Steinmetz index, and that's why so it belongs to less hysteresis loss.
Sir, what is rho H?
What is
Rho H or pH, whatever it is.
actually hysteresis loss? pH is the hysteresis loss.
Okay, okay, sir.
So whenever number of cycle is more, whenever frequency is more, so number of cycle is more, so then hysteresis loss is more. Whenever the volume of the specimen is more, then also hysteresis loss is more. And also the material property that is dictated by the coefficient of Steinmetz coefficient, as well as Steinmetz index. Another thing is that eddy current loss. Actually, whenever there is a coil, the coil also wound on a coil former. In case of electrical machine, this coil former is a core. So actually, core on the core there may have some slots. On the slots, the conductors are laid or coils are laid. So whenever there is a magnetic flux linkage in the conductor due to different types of magnetic flux linkage may be carried out. In case of transformer, also magnetic flux linkage is carried out due to the nature of alternating supply voltage or alternating flux linkage. That is called a stationary induced EMF. Means no part is rotating, but change of flux linkage is carried out due to the nature of the flux, alternating nature of the flux. That is the transformer induced EMF. And another thing is a rotational induced EMF, and that is carried out in the electrical machine. There must have some rotation either in the core, either in the armature or in the field. In some machine, field is static, armature is rotating. In some machine, armature is static, field is rotating. If the machine size is more, then the armature is more bulky, then armature is fixed and field is rotating. If the machine is less rating machine, low rating machine, then armature is not too bulky, then armature is rotating, field is comparatively bulky, and so field is stationary. So that is a rotational induced EMF. So whatever uh, change of flux linkage is carried out due to the rotation of the core or field, armature or field, or in sometime in case of transformer, that is the transformer induced EMF. There is no rotating part at all, but there is also change of flux linkage is carried out due to alteration of due to the reversal of the current or alteration of the current in the AC voltage and alteration of the flux linkage. So whatever it may be, uh, there may have change of flux linkage in the conductor, and also there may have change of flux linkage in the core also. The core is a magnetic material, so the change of flux linkage in the core, that is undesirable, but you cannot avoid this. So due to the change of flux linkage in the core, the current which is induced in the core, that is your eddy current. That is an undesirable current, but you cannot avoid this. But you can only avoid if you want to, if you can reduce this eddy current. How can you reduce this eddy current? As per the formula, the eddy current loss that is equal to some constant Ke, that is the eddy current coefficient, into Bmax square into T square F square into V. This is your eddy coefficient. This is your flux density, maximum flux density. And this is your thickness of lamination. Lamination is a term that is used, the thin sheets of material, that there may have some stacks of the material. So if you consider a core, if you consider a cylindrical core like this, if this cylinder is made by thin laminations are there. So in between this lamination, there may have some insulation. That is called the mica insulation is there. And then another lamination, another thin sheet, and then also mica insulation is there. So this is your lamination. And in between two lamination, that is your mica insulation. So cores are formed by a thin sheets of laminations, and in between two lamination there are mica insulations. When there is a mica insulation, the AD induced current that is flown in this core, that will be reduced because the insulation having more insulation resistance. So that is your Ke Bmax square T square F square into V. So this is your coefficient. This is maximum flux density. Mute. Lamination thickness. This is your frequency, cycle frequency. And this is your volume of the specimen.
So what are these laminations made up of?
Actually, lamination is actual material of lamination, say for electrical machine or transformer, that is your silicon steel, cold roll grain oriented silicon steel. And in between, these are the very thin sheets. As much as we decrease the lamination thickness, then also this eddy current loss is decreased. So it is our design criteria to make each lamination thickness smallest. So as much as you reduce this lamination thickness, then you can reduce the eddy current loss. And also the coefficient of eddy current, that also dictate the eddy current loss. So silicon steel is a kind of material that having coefficient is comparatively less than other material. So whenever you use the small thickness, you can reduce the eddy current loss. And for a silicon steel like material, the coefficient of eddy current coefficient is also less. And also the resistivity of the material, that also is comparatively more, and that will reduce the eddy current loss also. So whenever the current is flowing, eddy current is flowing, that eddy current loss is dictated by the coefficient, flux density, thickness of lamination, and the frequency of supply voltage. So whenever you can decrease the lamination thickness, or whenever you use such a kind of material having high resistivity and low eddy current coefficient. So high resistivity material means whenever the resistivity is more, the less current is induced in the core. So eddy current loss obviously is less. Whenever eddy current is less, eddy current loss is less. And like silicon steel, coefficient is also less. So normally it is done in case of transformer, very thin laminations, and each laminations are separated by mica insulation. So there are different stacks of laminations. one over another, in between two stacks there is a micro insulation. So this kind of codes are created, and different joints are also created. Different joints in transformer code, there is a butt joint, like joint construction is there. Whenever you study transformer, you will see different joints are there. This lamination should be stacked in such a way that uh, no loose construction should be there, because whenever AC current is flown through the circuit, there may have some vibrations, and if the loose fittings of these thin laminations are there, then uh, sound will be there. So whenever you go through in your locality, there may have some distribution transformers you have already seen. So whenever newly installed transformer you have seen that no sounds is there. But day by day, whenever these are old, say 5 years, 10 years, then you can hear some amount of sounds are there, and these sounds of the transformer, that is due to the vibration, and when the joints are due to low maintenance interval is more. So day by day, when the transformer is old, then the joints are becoming less, and the vibration sound is more. So whenever you pass through uh, a transformer, if the transformer is new, the sound is less, and old transformer having more sound. So this is your eddy current loss, and we have worked out some problems also, and different problems you have seen. You can easily understand this problem. Only formula based problems are there. Now today we will introduce another topic. That topic is electrostatics. Whenever I insert a page, actually the portion actually disturbed. Some of the written portion comes to another page also. I don't know whether I have already covered the footer portion. That's why it is or not. I think if I firstly insert a number of pages and then I write, and it will be better. Anyway, you must go through the different problems are there that already been done, and I have already uploaded this chapter magnetism, and you can see these workout problems also. Very simple problems, only based on formulas. Now electrostatics. I think you have already gone through these topics in your 10 plus 2 standard. So this electrostatics, that is a branch of engineering that deals with the charges, electrical charges. That is nothing but the flow of electron. That is your electrostatics. Whenever you understand that there may have some broad aspects of electrostatics, broad application of electrostatics. The important application of electrostatics are there. That is your some of the electrostatic generators are there that can produce voltage, very high voltage, electrostatic generators. In our Jadavpur University electrical department, there is a high voltage engineering laboratory. In this high voltage engineering laboratory, there 1 million volts electrostatic voltage can be developed. 1 million volt development capacity. So uh, there are different testings are carried out there. 1 million electrostatic voltage are generated there. This high voltage insulation testers are there. There are different commercial testings are carried out. So this one of the application of this electrostatic is electrostatic generators, very high voltage. These are used for X-ray work and sometimes nuclear bombardment also. Electrostatic principles are used in spray painting, uh, powder painting. The principles are used in pollution prevention. In you have I don't know you have heard or not. That is electrostatic precipitators are there. In thermal power plant, in a chimney there is electrostatic precipitator. Electrostatic precipitator precipitates the carbon from the flue gas. There is a huge application that reduce the pollution from the flue gas. Another example, the problems of preventing sparks and breakdown of the insulator. This high voltage engineering electrostatics are used. Sometimes the insulator is there, the insulator having very high voltage, very high resistance. So this through this high resistance, if you want to measure how much insulation resistance is there, so high voltage is required unless no current should be flown through this. If you want to know the breakdown strength of the insulator, then you have to increase the voltage. So one voltage will come. That voltage is sufficient to break down this insulation material. Means the current should flow through this insulation, and there is a measurement of breakdown strength of the insulation. Then high voltage is required. This static electricity is required. So this uh, electrostatic application is there to measure for breakdown strength of the insulating material. And another application is there, that is your lightning arresters. Electrostatic applications is there. Lightning arrestor, very high rising building. The lightning arresters are there. Whenever the charge cloud is passed, and if it is positively charged cloud and very high rising building, there is a electrostatic precipitator. Very sharp portion is there. So whenever the charge cloud is comparatively near, the medium in between this lightning arrestor and the charge cloud, the breakdown strength whenever it the charge cloud voltage is sufficient to uh, high breakdown strength in between, the voltage is sufficient, that is greater than the breakdown strength in between the medium, then the charge will come from the charge cloud to the lightning arrestor. So it will not become harmful for the building. And high amount of actually a leading, there is a, whenever you have seen the sparking, whenever thunderstorms are there, the sparking in the cloud, there may have some leading stroke and there may have some streamer stroke. Streamer stroke means whenever the breakdown strength exceeded the voltage in between this charge cloud and the lightning arrestor sharp particles, sharp point. The in between medium breakdown strength is the comparatively less than the voltage is generated. Then a leader stroke is coming from the charge cloud and a streamer stroke is coming from the uh, lightning arrestor. So it meets a point and then the sparking occurs and high amount of electric charge passes from the charge cloud to the lightning arrestor, and then lightning arrestor is arced to some point of the building So high amount of current that is passed through the earthing, and it saves the building. So this is the principle of the lightning arrestor. Um, so it saves the building. So different. Uh, this is a high voltage uh, subject, high voltage engineering. So it can describe how the lightning arrestor prevents the electric strokes. So these are different application of the electrostatics in engineering field. So now we will consider the basic law of uh, electrostatic. You know the Coulomb's law of electrostatics. There is a basic law of electrostatics. That law relates the nature of the force in between two charged particles. The first law that indicate the that relate the nature of the force in between two charged bodies, and the second law that tells about the magnitude of the force in between two charged body. So if the charge, you know that second law describes the force in between two charged body, that is Q1 and Q2. Two charged bodies are there, Q1 charge and Q2 charge, and they are separated by distance d. Then the electrostatic force, that force is proportional to Q1 into Q2 divided by d square. So that is equal to some constant k into Q1 into Q2 by d square. So this k, that is the proportionality constant, that is 4 pi. You know it very well in 10 plus 2 standard, into eta 0 into eta r into Q1 into Q2 by d square. So where eta 0 is the absolute permittivity of the air or vacuum, relative permittivity. Relative permittivity of the material where charge is there. So in case of air or vacuum, relative permittivity eta r is 1. So you know it very well in your 10 plus 2 standard. So here, according to Coulomb's law, this force, that is for the air medium, if the medium is air, so in between two charged particles, so this Q1 into Q2 divided by k means 4 pi, the eta 0, that is equal to 8.854 into 10 to the power minus 12 farad per meter. So if you put the value here, 4 pi into 8.854 into 10 to the power minus 12 into d square. So that is 9 into 10 to the power 10 to the power 9 q1 q2 by epsilon r into eta r into d square. So if the material having relative permittivity eta, now we have already known, 10 plus 2 standard, what is absolute permeability and what is relative permittivity, not permeability. Uh, the permittivity, that is a property of a medium, and that affects the magnitude of the force between 2 point charges. Actually, whenever permittivity is more, that is inversely proportional to the force. Whenever the permittivity um, of the field, electric field, that is more than the force of attraction or repulsion of the same charges. The same charge will attract, same charge will repel, and opposite charge will attract. So this uh, attraction force is inversely proportional to the permittivity. So air or vacuum has a minimum value, and in another material apart from air, there is a relative permittivity. So here the ratio of actual permittivity, that is equal to eta r into, sorry, eta 0. So relative permittivity, that is the ratio in between eta, that is the actual permittivity divided by absolute permittivity. This was already known in 10 plus 2 standard. Now electric field, the electric field that is created by the charged particle, just like magnetic field is created by magnet that may have some pole strength, an electric field having charges. So the field in which a charge experience a force, that is called the electric field. Just like a magnetic pole that experience a force in a magnetic field. So electric field that will force on the charge. So whenever a charged particle is placed in electric field, there is a force, just like a uh, magnetic pole coming in a magnetic field. So just like magnetic field, the electric field intensity is there, just like magnetic field intensity. So electric field intensity, that is the electric field strength at a point in an electric field. That is the force acting on a unit positive charge, just like a magnetic field intensity, the force acting on a unit north pole. So here the force that acting on a unit positive charge. So that is your electric field intensity. So if you consider there is electric field, and there is a unit positive charge. Say your unit positive charge means, so electric field that must have a charge. Say I am considering Q is the charge, plus Q. So if you take a unit positive charge, so that is 1 coulomb. So there may have some repulsion force, and that repulsion force that will be dictated by Coulomb's law. And if you consider the force, that force is Q into 1 divided by 4 pi epsilon 0 into divided by distance, that distance in between two, that is say d square. So actually Q by 4 pi epsilon 0 to d square, that is the force. So if you consider per unit charge, so if you consider this is your force, that force is the force that is experienced on the unit positive charge. So if you consider the unit positive charge placed in a near a electric field, so there is a force of repulsion. That repulsion force is Q into 1 divided by 4 pi epsilon 0 by d square. So this is eta 0 is the absolute permittivity of the medium. So force acting on Q coulomb, so that is force acting on unit positive charge. So for the force acting on Q coulomb charge, if it is F, then per unit charge, so for 1 coulomb charge, that is F by Q. If you consider the total force F, that is equal to Q 1 into Q2 by 4 pi epsilon 0 into d square. So per unit coulomb, this force will be equal to F by Q. So this F by Q is the field intensity. Per unit coulomb, the force experience, that is your field intensity. Now if you consider the electric flux, just like magnetic flux, so that is the electric lines of force follow outward from a positive charge. So you are considering that from the positive charge it is coming out, and that is the electric flux. And the electric flux that is E into A into cos of theta. So that is the electric field intensity. This is the surface area of the conductor where the electric flux is considered, surface area. And theta, that is the angle between the direction of electric field intensity and the normal to the area whenever there is a, so this is the angle between directions, that is a vector direction. Electric field must have magnitude as well as a direction. And normal to that area where electric flux is considered. Say a conductor is there. So you are considering a conductor, and conductor is, you take a conductor in an electric field. So electric field having a direction, and a normal to that conductor, there is also a direction. So in between the direction of electric field and the normal to the conductor area, that is theta. So normally electric flux will be maximum when theta will be 0, cos theta. So maximum electric flux when theta is equal to 0. That means the angle in between electric field and normal to the area is 0. That means perpendicular flux linkage on the conductor. If the machine is designed such that the flux linkage is perpendicular to the conductor, then the maximum flux linkage will be there. So machines are designed such that always there should have a perpendicular flux linkage with the conductor surface. So whenever theta is 0, so perpendicular flux linkage is carried out, then the electric flux is more, and more electric machine design criteria is based on this more flux linkage and more compact design of the machine. So whenever more flux linkage is there, more torque is experienced, and torque per weight ratio is comparatively more. So design criteria is the torque per weight ratio of a electrical machine. So whenever torque per ratio is more, means torque is more per unit weight of the machine. Whenever weight of the machine is less, that means machine design is more compact in size. So electric flux, that is minimum. So that is equal to 0 whenever theta is equal to 90 degree. That means surface is parallel to the field. It is never done. The surface is parallel to the electric field. So whenever electric motors are designed, these are the conductors, and this is the magnetic pole. This is a N pole, then this is S pole. Always flux linkage. This is your conductor, and this is your core. So whenever electrical machine is designed, always the flux linkage, flux is linked just like in this path. So it originates from the N pole and terminates to the S pole, just like this path. So whenever flux linkage is carried out in the conductor, that is perpendicular flux linkage. This is a design principle of the machine, electrical machine design. So maximum flux linkage and torque per unit ratio of the machine is more, and then more compact design, lighter weight electrical motors are designed. Now electric flux density, that is the flux per unit area. So electric flux density D, that is equal to flux per unit area. Coulomb per square meter. So whenever you consider the relation between D and E is the electric field intensity and D is the electric flux density. So if you consider a positive charge Q and such a point at D distance, you are considering a point P. So the electric at a P point you are considering the field intensity. So flux density at the P point, the value of the flux density at the P point, D at P point, that is equal to plus Q divided by 4 pi d square as per the Coulomb's law. So you are considering here unit positive charge. So unit positive charge having 1 coulomb charge. So a force experience, that is 1 by 4 pi d square. Sorry, you are considering here actually flux density, force per unit area. So force per unit area, if you consider the flux linking is carried out, so if there is charge is there, if you consider here, so flux linkage is carried out at d diameter. So d is the distance, sorry, d is the radius of the flux path. So here q by 4 pi d square is the flux density, and electric field intensity E, as per the Coulomb's law, if you place a unit positive charge at P point, the force experienced by the field to this unit positive charge, that is your q by 4 pi d square into 1 by epsilon 0 epsilon r, eta 0 eta r. That is as per Coulomb's law. So relation in between D and E, that is your E is equal to d by eta 0 eta r.
Sir, could you please explain the D relation once again?
So actually I am considering a positive charge of plus q here. And at P distance, at P point, that is at D distance, I am considering a unit positive charge. So if I consider firstly the electric flux density D, so that is q by 4 pi d square. So that is your surface area. So whenever flux is created over the surface area of the sphere, so it is considered, so the distance is d. So the flux per unit area of the surface area of the sphere, so having d diameter, d is the radius of the flux path, then the flux, that the charge per unit area, surface area, that is 4 by d square. And similar way, as per definition of the electric field intensity, if you consider a unit positive charge at a point P, the force experienced on the unit positive charge due to a charged particle plus q, that is q by 4 pi d square into 1 by epsilon 0 epsilon r, as per this Coulomb's law. So E is equal to d by 4 pi epsilon 0 epsilon r. So electric field intensity and electric flux density, there is a relation.
Sir,
Yes.
sir, D is the charge density, not the flux density.
Capital D is the
Charge density, na?
actual charge density or electric flux density are same. So magnetically, if you are considered flux density, but electrically, if you consider the charge density, that is nothing but the electric flux density. Understand my point? Electric flux is nothing but the electric charge. So it is termed electric flux density. Understand my point?
Sir, it is still not clear, sir.
It will be clear when you consider the Gauss theorem. Actually, electric charge is not other thing from the electric flux. Whenever you consider electric charge, that is nothing but the electric flux. So in case of magnetic field, the magnetic flux is there, but magnetic charge is not there. But electric charge is analogous to the electric flux, just like magnetic flux.
Okay, sir.
Whenever you consider Gauss theorem, I think you have already studied Gauss theorem.
Yes, sir.
It was first expressed by German scientist Carl Friedrich Gauss. So this theorem states that whenever there is electric flux passing through a closed surface, means electric charge. In your term, that is electric charge. A number of charge is equal to the algebraic sum of the charges inside the closed surface. And the shape of the surface and the location of charge inside the closed surface are immaterial. Whatever shape of the surface is there. So you are considering a charge is there. So you are considering a charge plus q is there. And the point charge q lying at any pole position, or you may consider the center, and the shape of the surface, the location and the surface shape of the surface, that is immaterial. Then the theorem states that the total flux or electric charge that is coming out from the surface, that is equal to total algebraic sum of the charges inside the surface. So if you consider that q charge is there at any point, so the flux, you can consider the electric field intensity due to this charge, that is E, and the surface area, that is A. If you consider the center, firstly, if you can consider there is a spherical shape, but the theorem states whatever surface is surface shape and the position of the charge is immaterial. So if you consider the spherical shape, plus q charges is there, and electric field intensity due to this charge, that is E, and having the sphere having radius r. So electric field, actually the total electric flux, that is equal to electric field into surface area. So electric field that is created due to the charge q, that is nothing but q by 4 pi epsilon 0, I am considering the air medium, eta 0 into r square into surface area of the sphere, that is 4 pi r square. So actually that is q by eta 0. So mathematically, if you consider the Gauss theorem, then mathematically you can express this Gauss theorem. That is your surface integral of the normal component of the electric field intensity. That is equal to q by epsilon eta 0. So actually, you know, En that is equal to dn divided by eta 0. So mathematical expression, so that is equal to surface integral of this En. So that is your En into beta 0 ds, that is equal to q. So closed surface integral of dn, that is equal to q. So the total charge coming out from the closed surface is equal to total flux. dn is the electric flux, normal component of electric flux. The total surface integral of dn means the total flux coming out from the total electric flux coming out, or rather in your term total electric charge that is coming out. So here it is termed as total electric flux coming out from the closed surface, that is equal to total charge enclosed by this closed surface. So that is nothing but the algebraic sum of the total charge. If there is a number of charges are there, we can consider a number of charges are there, you can consider that total flux coming out, that is equal to algebraic sum of the total charge enclosed in that surface. So total, according to Gauss theorem, the total electric flux coming out from a closed surface, that is equal to the algebraic sum of the total charge enclosed. It is immaterial to the position of the charge and the surface of the material where charge is considered, where flux is coming out. So it is immaterial to the surface type and the position or location of the charge inside. So total electric flux coming out, normal component of total electric flux coming out from a closed surface is equal to total charge enclosed in that surface. That is your Gauss theorem. Now, I am coming to the concept of the capacitance. Actually, capacitance is the capacity of flow of electric charge through a dielectric. If there is a dielectric material and you are subjected, you are applying some amount of voltage here, so there may have some dielectric medium. So capacity of the dielectric medium to flow the charge from one point to another point, that is your capacitance. So any two conducting surface separated by insulating material, this is called the dielectric. Insulating material. So that is your that is called the conductor or conductance. The capacitance, that is the conducting surface. These are the plates, and this is your dielectric. So ability of the capacitor to store charge, that depends on the area of the plate, distance in between plate, and the nature of insulating material or the dielectric uh, medium permittivity. So different dielectric medium have different permittivity. So capacitor is generally named after the dielectric use, that is the air capacitor or paper capacitor. If the capacitor is dielectric, the dielectric medium is air, then it is air capacitor. If the dielectric medium is paper, then it is paper capacitor. Sometimes dielectric medium is mica, then it is mica capacitor. So as per the dielectric named capacitor names are there. but the shape of the capacitor are different. So parallel plate capacitor, just like parallel plate capacitor, you are just applying some amount of voltage here. So if you connect this to a battery plus point, so V is the voltage, then positive charge are induced here and the negative charge are induced here. And when the capacitance charging is there, so positive charge are stored here and the negative charge are stored here. So there is a flow of charge in between the capacitor. When the discharge is there, then the positive charge is flown, just like it forms just like a battery. Positive charge is flown to a circuit. That stored charge is flown to a circuit. So the charge which is stored here, that Q charge, that is proportional to the applied voltage V. Whenever you increase the voltage, then more charge will be induced in the parallel plate. So this proportionality constant, that is your C, that is called the capacitance. So V, the applied voltage, that is equal to the charge by capacitance, Q by C. So whenever capacitance is more, then for a specified voltage, the induced charge is more. Whenever capacitance is less, then induced charge is less. So capacitance is the capacity of the capacitor to store the induced charge. So more capacitance will store more charge and less capacitance will store less charge. Now you know the electric flux density, that electric flux density D, that is equal to epsilon into E, that is the permittivity. This epsilon, that is equal to epsilon 0, eta 0, or rather you can term that eta, epsilon, that is the permittivity, total permittivity, eta 0 into eta R. But this D electric flux density, that is, you know that electric flux is nothing but the electric charge. So that is your Q divided by A. The A is the effective area of the parallel plate capacitor, parallel plate effective area, and D is the flux density, Q is the stored charge, and E is equal to, you know from the previous formula, that D by epsilon. So that is your D means Q by A into epsilon. So you can consider whenever there is a parallel plate capacitor and the plate capacitor having a distance D, if I consider the distance in between this plate capacitor, that is parallel plate, that distance is your D, and the surface area of the plate, that is your A, and the permittivity of this medium, that is epsilon. Then your voltage across this capacitor, if you consider there is a charge Q has been already stored here. Induced charge is Q that has already been stored, and voltage source is not there. Now capacitor is a stored capacitor, where Q charge has been induced and separating distance of the plate capacitor. Now, if you consider the potential difference in between uh, two plates, then the potential difference between two plates, say if you consider this in between two plate, this is say A point and this is say B point. So potential in between two plate, that is V suffix AB, if you consider for a stored capacitance. So VAB, that is line integral of the electric field intensity, that is termed as line integral, but this is nothing but the field intensity into the distance over which you are considering the integration limit, that is A to B point. So in between two electric field intensity into the length, effective length, separation distance. So that is nothing but E into D. D is the separating distance in between two plate. So actually E is the Q by A epsilon into D. So actually that is equal to Q by epsilon A by D. So you know that voltage, that is equal to charge divided by capacitance. So magnitude of the capacitance, that is nothing but epsilon A by D. So the permittivity of the dielectric medium dictate the value of the capacitance. Similarly, plate area, that also dictate the capacitance, parallel plate area, and the separation distance of this parallel plate, that also dictate the value of the capacitance. So if you consider the charge Q, if you consider the charge Q, so I insert a separate page. Whenever I insert, some of the portion coming another page. Whenever you consider charge Q, that is equal to capacitance into voltage. So dq dt, that is the current, that is equal to C into dv dt. So the current I, that is equal to C into dv dt. So you can consider that dv, that is equal to 1 by C integration of I dt. So definition from the potential of a point, that is nothing but bringing a unit positive charge from infinite point to that point, the work done by the unit positive charge. So if there is a electric field, if you want to bring if you want to measure the potential of a point, by definition that is nothing but the bringing a unit positive charge from infinite point to that point, the work done, that is nothing but the potential of that point. So potential of that point, so the potential limit becomes 1 by C minus infinity to T. So whenever current is time varying, voltage is also time varying. So after that is 1 by C integration of minus infinite to 0. So actually time instant is splitted into two parts. One is the infinite to the infinite timing to a specific timing whenever you are considering, and then that initial timing to a certain finite timing.
So why minus infinity?
Because whenever you consider that some instance that is before your consideration time, so whenever you consider a specific timing, that is zero instant. Whenever you consider infinite time before, so then minus infinite. T is equal to minus infinite. Because I am considering this fact that some amount of charge already been stored in the capacitance at infinite time before, mathematically. And then you are considering at zeroth instant timing, so when t is equal to 0, you are considering the amount of charge.
So if some charge is already stored, sir, before zero time, so that means we can consider that time, sir, that charge from the zero time only, sir. Then what's the need of taking it from minus infinity?
So actually, whenever you are splitting a time instant, you are splitting a time instant. So this is your zeroth timing, t is equal to 0. So there is a charging, but if you consider there may have already charged, so your consideration time will be from this point. So already been charged before the instantaneous time. So I am considering that potential of a point that is described as bringing a unit positive charge from infinite to infinite distance to that point. So if I consider the time splitting from the infinite time before the original timing, there may have some effect. That effect is considered in time. So infinite time to zeroth time, there is a charge, and from the zeroth time to a certain specific time, there is the charge which is being stored. So 1 by c integration of minus infinity to it, that is termed as 1 by c into q0 plus 1 by c integration of 0 time to t time it dt, that is 1 by c into qt. So this is the stored charge. Current is the rate of flow of charge. So integration of current dq dt, that is equal to current. So integration of q dq, that is equal to charge, that is equal to integration of time. So integration of time is nothing but the charge. So some portion of the charge that is already been stored in the capacitor, that is the stored charge, plus some portion of charge that the capacitance have acquired for teeth timing. Acquired charge for T timing. So some portion is already stored charge and some portion is acquired charge. So the total potential that is considered in terms of stored charge and also acquired charge. So if you consider the time varying current, if you consider the time varying current or time varying voltage is there. So you have to consider that IT, the time varying current, that is equal to C into dV by dt. So that is equal to C into ddt of Vm sin omega t. So V is equal to Vm, the maximum voltage, into sine of omega t, that the angular frequency of the supply voltage. Omega is the angular frequency of the supply voltage. V is the maximum voltage. So if the voltage is alternating in voltage, alternating in nature, like this. So this is your omega t and this is your voltage magnitude Vt. So this voltage is applied in a capacitor, to a capacitor. So actually current which is flown, that is equal to C into dV by dt. So here CVM cos omega t, C into Vm cos omega t
Sir, into omega.
into omega. So actually that is Vm divided by 1 by omega c into sine of omega t minus sine of omega t plus pi by 2. So that means that is equal to Vm divided by Xc. Xc is the capacitive reactance into sine of omega t plus pi by 2. So if you consider this is the current IT, so that is IT is equal to I max into sine of omega t plus pi by 2. So if you consider the phasor representation of the capacitive current, if the voltage phasor is like this, that is Vt, the current phasor will lead the voltage phasor by 90 degree. IT. So phasor leading means if you put an eye here, so this phasor is just rotating. So first of all you meet IT and then after pi by 2 angle representation you meet Vt. So Vt is phase lag by IT by 90 degree. So IT is phase lead by Vt by 90 degree. So always pure capacitance having a phase leading current that of the voltage by 90 degree. Now if you consider the capacitance on isolated conducting sphere,
Sir, can you please show the graph again? A phasor diagram or whatever.
actually this is very simple graph. Whenever you are considering say voltage phasor and current phasor, so for a pure capacitance in the circuit, I have already explained that when Vt is equal to Vm sine omega t, then it becomes Im sine omega t plus pi by 2. That I have already derived. So that means current phasor is 90-degree leading. This is your current phasor and this is your voltage phasor. So whenever the phasor is rotating in this direction and your eye is there, so you can see first you are meeting the current phasor, then you are meeting voltage phasor after 90-degree phase lag. That means voltage phasor is phase lag for a pure capacitance 90-degree phase lag, and current phasor is 90-degree phase lead that of the voltage phasor. Understand my point?
So what is the physical significance of it?
Physical significance is that the capacitance current phasor always lead the voltage phasor. Physical significance, you have to consider, say, alternating in nature of voltage like this. This is your voltage phasor. If you consider the current phasor for a pure capacitance, then you will get like this. Whenever it is 0, then it is maximum. Whenever it is maximum, then it is 0. Whenever it is 0, then it is maximum. Whenever it is maximum, then it is 0. When like this. So current phasor, this is your current phasor IT, and this is your voltage phasor VT. So voltage phasor always phase lag that of the current phasor by 90 degree. So this is your pi and this is your pi by 2. So current phasor leads the voltage phasor by 90 degree for a pure capacitance. Just like for a pure inductance, voltage phasor always lead the current phasor than that of the voltage phasor always lead, current phasor always lag. If this is a voltage phasor, then for a pure inductance, the current phasor will lag. Means whenever it is 0, so it will lag, just like whenever it is pi by 2, like it is pi, then the phasor will lag by 90 degree. If you consider here, so current phasor will lag by 90 degree, means if this is a voltage phasor, then in case of pure inductance, the current phasor will lag by 90 degree, means it will start from here. Just like. So this is your, so actually this is your fundamental voltage phasor and this is your current phasor. Whenever it start 90 degree, this is pi by 2, this is pi, this is 3 pi by 2, this is pi. So here also this is pi by 2 and this is pi. So current phasor starts like this. This is your voltage phasor and this is your current phasor for pure capacitance. And for pure inductance, the current phasor, say I can say that this is your pure capacitance current phasor IC, and for pure inductance current phasor, that will 90 degree lead than the voltage phasor. Voltage phasor is a fundamental phasor, and current phasor leads 90 degree.
Sir, I got it.
You got?
Yes, sir. Thank you, sir.
Just like. So in case of, this is your IC. So in case of pure inductance, that is IL T, that is equal to Im into sine of omega t minus pi by 2. So I think this is up to today's class. Lot of topics are due. Syllabus is way more. So I have to take more classes.